So I welcome all of you, boys and girls. In this video, we discuss a little bit about defects. Do you know any person who is not having a defect? However perfect he is. Seems only the legendary characters, great people in stories appears to be defectless. Heroes in some cinemas. But in real life, nobody is free from defects. A deviation from orderly arrangement of particles is said to be defect. In solids, true solids, they are supposed to have long range and short range order in the arrangement of particles. If that specific rhythm is disturbed in some pockets, some areas, some points, then the deviation from orderly arrangement is called defect. There are two types of defects which we can see. They are called stoichiometric defects, where the formula of the compound is maintained, no deviation in the formula. And the other variety is non-stoichiometric defects. If a compound is having non-stoichiometric defect, it no longer has a formula which we originally think that it has. For example, iron oxide is available in nature as wostite. This wostite is supposed to have a formula FeO, is not really FeO. It appears to be like Fe.960, Fe.950, no different formula. Such variation is caused by non-stoichiometric defects, about which we discuss in the next video. Now quickly we see the stoichiometric defects are also known as intrinsic or thermodynamic defects. And in this there are two variants. One is called vacancy defect and the other one is interstitial defect. In vacancy defect, some fellows will be missing. If we have a covalent molecule like AB, as many A's are missing, as many B's are missing. Due to such missing A and B's in the overall solid, the formula or the composition remains the same, but the compound will have lower density. Interstitial defect means one A will be missing from its place and getting itself locked in gaps between the particles. These gaps are called voids or interstitials. And now, the vacancy defects decrease the density because so many A's and B's are missing, and such defects can be developed by heating. Whereas interstitial defects can increase the density because in this place where you are supposed to have vacancy, some fellows are sitting. This is shown, these two defects, vacancy defects and interstitial defects, are shown by non-ionic compounds. Now, if you are talking of ionic compounds, these vacancy defects are similar to something called Schottky defects, whereas interstitial defects are similar to what is called as Frenkel defects. The Frenkel and Schottky defects are shown by the ionic compounds. Now, let us look at the Frenkel defect. This is also known as dislocation defect. This is shown by ionic compounds where the cation and anion differ greatly in their sizes. For example, if you take AgB or AgI, I minus is very big, Ag plus is very small. And ZnS, Zn plus 2 is very small, S minus 2 is very big. Such fellows can show Frenkel defects. Here what happens is a cation, the Zn plus 2, Ag plus, the coordination number also appears to be not very great, and the Zn plus 2 Ag plus will slip from its position and get itself placed in gap between the particles, anions which are making the lattice. This position, that is a gap between the anions which are making the lattice, is called void or interstitial, where the cation will be sitting. Okay. Now these defects do not affect the densities. So coordination number is less. These are the examples of the Frenkel defect. You can see one fellow is missing its position and getting itself locked in the gap. For example, if there are 30 girls and 30 boys in a class, one girl misses her place and sits below the desk of the teacher, simply to play a prank. It means the number of girls and boys in the class remains same, but one girl appears, she is not there, but she is actually under the desk. She is hiding herself, or a boy is hiding himself, like that. So they do not affect the densities, of course. Now looking at the Schottky defects, Now, Schottky defects are involving loss of equal number of, or they involve missing cations and anions in equal number, and such defects decrease the density of solids. If you take sodium chloride, in sodium chloride coordination number is 6:6, and here the Na plus and Cl minus ions have comparable size. If you take 1 centimeter cube of sodium chloride that contain about 10 to the power 22 ion pairs, it shows 10 to the power 6 Schottky defects. It means there is one Schottky defect for every 10 to the power 16 ions. This type of defects will decrease the density of the solid you are considering. This is shown by NaCl, KCl, cesium chloride, AgBr, etc. Very, very interestingly, AgBr can show both the Schottky defects and Frenkel defects. Okay. Now about the non-stoichiometric defects we discuss in the next video. Please notice these are very important aspects about defects. Okay. Thank you very much. Pause the video and see it several times.